Alright, so in figure 1 shows the density of liquid water as it changes with temperature. So check out the liquid water. It actually gets denser as you goes from 0 degrees Celsius. It gets denser, and then as you go up higher, it gets less dense. That's interesting. Alright, and then figure 2 shows the density for solid water. What is solid water known as? Ice. There we go. This is ice. And ice apparently gets denser as you get colder. Notice how as you get colder, the ice gets denser. Which is actually why you ever put ice cubes inside of your water? Inside of your regular water? It actually, your ice cubes float, and that's because your ice cubes, the density is actually kind of down here over here. So on average, your ice cubes are going to be colder than your water, so then they'll be down here. That's why your ice cubes float. Does that make sense? But apparently if you have super cold ice cubes, they'll kind of sink, which is interesting. Or, you guys ever go to a bar and order like a really hard liquor drink and put ice cubes inside? Of course not. Of course not. You guys aren't alcoholics. But anyway, what I'm saying is, if you ever notice, like, you got to be 21 and above, not 18 and above. But if you ever notice that, like when people put ice cubes inside of, like, you know, like you see the commercials where they put ice cubes inside of the rum or whatever, those ice cubes fall straight to the bottom. They don't sink. They don't sink. Anyway, I thought it was interesting because those ice cubes fall straight to the bottom. It's because alcohol is not as dense as water. For example, alcohol only has a density of 0.79 at 4 degrees Celsius, or at 25 degrees Celsius. Interesting, huh? Anyway, let's do the problem. So that actually had nothing to do with our thing. So yeah, and actually I don't drink at all, so I have no idea. I only noticed this thing because, yeah, I mean, I hang out with people in college and whatnot, but it's not that I like ever drink. I don't really drink anything at all. I think on since I turned 21, that was almost 10 years ago, I can count on one hand, maybe two. I can count on two hands how many things of alcohol I've ever had. Yeah. Anyway, all right, moving on. I'm a robot. All right. According to Figure 1, as the temperature for the liquid of water increases. All right, wait. This part right here I drew in, so this isn't right here. All right. But according to Figure 1, as the temperature of water of the liquid decreases from 10 degrees Celsius to 0 degrees Celsius, what happens to the density? So as I go from here to here, I'm decreasing, right? What happens to it? It goes, don't worry about it, Nolan. You didn't even hear the question, and now you can answer the question. Which one is it? 25, number 25. As the temperature decreases, it goes where and then where? The density does what? It increases, increase, and then it decreases. There we go. Increases, then decreases. Option D. That's it. All right. A student claimed that if one mass of 1 centimeter cubed of any solid and 1 centimeter cubed of any liquid are compared, the mass of the solid would be greater. All right, without even looking at the options, is that true? Yes, you say that's true. Maybe not. I don't know. Can you ever think of any situation where solid is actually lighter than a liquid? Can you think of any solid that floats. Wood. Wood floats. Ice floats. So therefore, this is not true. This right here, that's, I mean, the student is wrong. You know what I mean? Yeah. I float. I can float. Wood floats. Foam floats. So, these two yes statements are wrong right off the bat. I mean, we didn't even look at the data. We just said, the student says that any solid is going to weigh more than any liquid if you have the same amount of stuff. That's not true. Alright, anyway, let's look at the table. Is there a solid over here? So like, this density is 5 grams per centimeter cubed, right here, or 5.73 grams per centimeter cubed. So if I had 1 centimeter cubed, how much would that weigh? 5 grams, exactly. Okay, now I got a question. Would all of these solids be heavier than all of these liquids? See these liquids? No, and why not? Because of mercury. Mercury is the king. Mercury actually beats out lead. Mercury is denser than lead. Isn't that crazy? Like here, I'll show you how crazy that is. I wasn't even actually going to do this, but I think I will, just because I think it is kind of cool. Let's try this. I'm going to look up cannonball on lead. Okay, sorry. Google Chrome is deciding on whether or not it wants to work. Alright, there we go. Cannonball floats in mercury. Let's look up a video, because I think it's awesome. You actually have a cannonball, a lead cannonball, and they put it in a vat of mercury. Now, you're right, a vat of mercury is a little poisonous, so let's kind of stay away from that. But anyway, you put it in a vat of mercury, and the thing floats. It's crazy. Here's a 25-second video. Let's watch it. YouTube. And I'll share the link with you guys, because it'll probably be glitchy when I play it. I can't hear him. Hold on. Let me play it. Let me share you guys this link. I'm gonna throw up this guy a couple times. I'm gonna spam him, and then click on that. Click on that link, and then watch it. It's only 25 seconds long. I don't know what he's saying though. Here, I'm going to put a ball of lead inside of mercury and watch it float. It's going to be amazing. It's because of the density. The density of this ball is going to float in that thing of mercury. Isn't that cool? A cannonball floating on mercury. That's crazy. That's kind of crazy. Anyway. Bazinga-bing! Yeah, exactly. Alright, but that doesn't have anything to do with this. Alright, so anyway, yes, you're right. It's because mercury has such a high density, so the answer is G. This student's claim is false, and the reason being the student's claim is false... Wait, what was the top comment? I didn't read that. Yeah. Where does he get that much mercury? I don't know. These guys are chemists. I mean, that's what they do. But anyway, the reason why it's false is because mercury is higher density than anything else. All right, which of the following hypotheses about the relation between the temperature and density of a solid is best supported by Figure 2? Okay, As the temperature of the solid increases, the density of the solid does what? Look at figure 2. As the temperature increases, what happens to my density? Come on, I need you guys back. We're going to have to get back so that we can... It decreases. There we go. And it only decreases. I could talk about these all day, but I choose not to. But you're right. It decreases only. Let's move on. Equal amounts of ethyl ether, mercury, and water, all at... Okay, what is a water? A water has this density at 25 degrees Celsius. Are poured into a single beaker, and 3 distinct layers formed in that liquid. Based on Table 1, what is the order of the from top to bottom of the liquids in the beaker? Now, I got a question. What liquid will sink to the bottom? Ethyl, mercury, or water? Gainsborough Barons, which one will sink? Mercury will sink to the bottom. Why? Because it is the densest. We talked about it. Okay, good. So mercury will sink. So that kills these two guys. Because you're going to have mercury at the bottom of this thing. Now, which one will float the most? Which one will be on top? Water or ether? Water or ether? Well, which one is less dense? The water has a density of 0.9971. The ether ethanol has a density of 0.71. So which one will float the most? The ethyl. So therefore, this is your answer. It is that easy. Are we cool with that? We cool. Alright, good. Next one, 29. According to figure 1, let's look at figure 1. There it is. 100 grams of water at 4 degrees Celsius would exactly fill the container having which of the following volumes? Okay, so the question is how much volume is these figures going to have? Alright, how do you figure out volume? Well, if you have the density, which we label as rho, is equal to mass over volume, then if you want to figure out how much volume you'll have, you just say volume is equal to mass divided by density. Do you guys see that? Oh, by the way, this rho looking thing is density. Because I'm going to multiply both sides by volume, and that takes him up here. I'm going to divide both sides by density, and that takes him down there. That's basic algebra. You guys know how to do that. So, what is the density of water at... What is the density of water at 4 degrees Celsius? It's 1.000000000. Good. So, 100 grams of water is going to take up how much? 100 grams of water is going to take up how much volume? That would be 100 grams divided by 1 gram per centimeter cubed. What's 100 divided by 1? 100. There we go. That is the answer. That's as simple as it gets. Does that make sensey? Now, for that one alone, you actually did need to know a little bit about science, although at least they told you what density means. It's mass, density is mass over volume. But you would need to know a little bit about density in order to pass that. So, remember how I told you don't need to know anything about science? Well, yeah, you do. You kind of got to understand a little bit of what density is. But that's, like, you learned that in 4th grade, I think. But anyway... Sophia, did you have trouble with that one? Do you want me to explain that again? Alright, anyway, well, here's what it is. The density of water at 4 degrees Celsius is 1.000, and it's in grams per centimeter cubed. 1 gram for every centimeter cubed. So if I have 1 gram of water, it will take up 1 centimeter cubed of volume. If I have 100 grams of water, that should take up 100 centimeter cubed of volume. That's it. That's all it is. Does that make sense now? Alright, I gotta move on to the next part, because we've been talking, all we do is talk story, and that's no good. Alright, if it said that in the problem, I'll talk to you after, and that way we can get done with our class, and I'll talk to you after that. Alright, we only got 20 minutes to finish the rest of this stuff, and the problem is, we took like half an hour to get through the first one, so 20 minutes to get through 2 of them. Okay, let's do it. The clearing in a rainforest results in forest fragmentation, the breakup of large forest tracts into smaller patches. Got it. Researchers predicted that the fragmentation would result in a decrease in animal population and the above ground tree biomass, AGTB, and in the resulting fragments. They did 4 studies to test this prediction. All right, good. The researchers monitored the AGTB in 25 100 by 100 meter forest plots near the areas had recently been cleared of vegetation. The distance from the center of each plot to the nearest clearing was measured. Figure 1 shows the average change per plot in AGTB in metric tons per year over 17 years. Okay, got it. Study 2, 25 100 meter by 100 meter plots were monitored in Study 1. The center of each of these plots at least 500 meters from the nearest clearing. The average change in AGTB over 17 a year for these 25 years plots. Okay, I don't even understand that, Study 2, but alright, whatever. Researchers monitored 16 100 meter by 100 meter forest plots near the areas that recently cleared in vegetation. Each plots were bordered on one side by a clearing. Figure 2 shows the average cumulative percent change in AGTB at these plots following fragmentation. Okay, so that's figure 2. It's the average cumulative percent change in AGTB per year. I have no idea what I'm talking about here, but let's finish this off. Researchers trapped the released birds in 10 forest fragments adjacent to areas that have been recently cleared out. The insectivores, the frugivores, those are fruit eaters, and the hummingbirds. Figure 3 shows a number of captures in per 1,000 hours of trapping. Okay, so what it's saying is basically, if you kill the forest, it's bad for the insects. Does that make sense? If you kill the forest, it's bad for the insects. Because look, if you kill the forest, the insectivores, the population goes down. If you kill the forest, the frugivores, that population goes down. And if you kill the forest, the population of the hummingbirds goes down. Actually, wait. Does the hummingbirds go down? No. Huh. I don't know why. Alright, whatever. It goes up. So let's try this. In Study 4, as time increased from year 0 to year 6, the captures of frugivores did what? Alright, Study 4. From year 0 to 6, the captures of frugivores did what? Did they increase, decrease, go up, go down, stay the same? What do they do? They increase because the frugivores are the one in the middle, and they still look like they decreased. Frugivores. This is a decrease. And you guys are asking, when is this due? It's not due. This problem, this homework, this thing that I'm doing for you is not due. It's this is just my example problems. I'm just doing the example problems. Like I was supposed to do 7 of them, and I'm doing 3 of them. I'm doing the last 3 because I spent the last 2 weeks doing the example problems. So this is for when you're a junior in high school, but this is also for a test that you're going to take called the Explorer, which has a science part of it. So I'm teaching you to the high school level, even though you're in the 8th grade level. And the reason being is because I'm trying to actually show you that, like, this high school level questions can be answered when you're in 8th grade. Yes, and that means you guys are incredibly smart. All right, based on the results of study 4, how did the fragmentation most likely affect the population sizes of insectivores and hummingbirds in the fragment studies? Okay, look at chart number 4. I'll copy and paste it for you. Copy and paste. Alright, here's chart number 4. Based on chart number 4, the fragmentation, what did it do to the insectivores and the hummingbirds? So, it increased the population sizes for the insectivores and hummingbirds. No. The insectivores went down drastically. The fragmentation decreased the population of both insectivores and hummingbirds. No. The hummingbirds actually went up. The fragmentation increased the population size of the insectivores. I'm going to say no right off the bat because look at the insectivores, they went down. So the answer is D, and that's it. That's all it is, D. Because the insectivores decreased and the hummingbirds increased. Does that make sense? All right. Based on the results of the study in 1, if the distance from the center of a 100 meter to 100 by 100 meter plot was 75 meters from the nearest clearing, the expected average change of AGTB would be closest to which? Okay, fine. Let's go to the chart. We have our chart. We're going to 75 meters. That's over here, right? What would you expect the AGTB to be? About -2.5. It's basically between -3 and -2. I agree with you. The answer is G. It's the only one that is between -3 and -2. That's it. Make sense? Alright, next one. After examining the results of the study 2, the students concluded that the AGTB for each of the 25 plots remained constant. The following alternative explanations are consistent with the results. Alright, so we're looking at study 2 here. That's this guy right here. And this one says, actually, you know what? I don't have a whole lot of time, so I was almost going to skip this one. But, alright, let's do it. The study says that all 25 plots increased. Did they all increase? No. Increase would look like that. Did they all decrease? Yes. No, actually it doesn't. Yes, pretty much. Yes, pretty much, but it's not exactly true. Because over here it didn't decrease. So that's out. The AGTB at some points of the plot increased and some points decreased. Alright, so for the most part they decreased. and they didn't really increase. However, I would say that this is your best answer, and that one's a little bit tricky. Because the graph kind of looks like this. It decreases, but it doesn't decrease at every plot. You know what I mean? So I would say that it's a lot better answer than B is. And D, it says the plots by the forest increased and the AGTP routes bounded by the clearings remained constant. Yes, but I would say D is out because they said the plots increased, and they didn't increase, they decreased. So C kind of gives you the most range. Alright, so I didn't like that problem. That question was a little weird. Which of the following results, or set of results from the studies, is the least consistent with the prediction of the proposed by the researchers? And the prediction proposed by the researchers is basically, as you kill the forest, the animals will die. The birds will die. So, which one goes against that? What study goes against that? Was there something funky in this thing? And yes, Nolan, this is practice for your final test. Your final test is next week. The hummingbirds. Exactly. Because notice how the hummingbirds, as you killed the forest, the hummingbird population actually went up. Didn't ask you to explain that, just said that's what it is. Alright. Last one. In study 4, the researchers trapped birds for 10,000 hours per year. Thus, how many insectivores were trapped in year number 2? So, let's look at the picture. Year number 2. This is year number 2. How many birds were trapped in year number 2? 80. For the insectivores, that is. 80. So the answer is 80. Everyone agree? Everyone's wrong. You got close. Look at it closely. I'll tell you what, I'll copy and paste that thing underneath right there. Look at the graph. This is actually kind of important because I want to show it to you. It's not a trick question. Ah, Vernon sees it. They went for 10,000 hours. This is how many birds you'll capture every 1,000 hours. So therefore, if you went for 10,000 hours, you would catch 800 because it's 80 times 10. You gotta be careful with that kind of stuff. Does that make sense? No, it's not really a trick question. You just gotta read it carefully. But they will burn you on that if you don't get it. So, careful with their tricks. Alright, I'll tell you what. You guys are released to go. You guys can leave now if you want. I will cover this last one just because I think it's important. And it will probably take me about 10 minutes to do so. But you guys are released to go if you need to. You guys can stay if you want, or you can go if you need to. It's fine. If you have a question, I'm fine with that. Peyton, I got your mom's email. And it's something about like I need to grade your assignments. I'm sorry that I didn't grade your assignments. I'm working on that now. I'm trying to grade everything like phonetically. Is that what your question is? Okay. You guys can ask your question, but let me finish this thing first. All right. Okay, let's do this question real quick, and then we'll go. Hopefully I can take 10 minutes, and I'll stop the archive, and I'll answer any questions. Glaciers deposit till. What is till? A poorly sorted sediment. If glaciers repeatedly advance over an area and then melt back until the till deposits may form. Figure 1 shows the vertical core taken through the layers of till of non-glacial sediments and bedrock in sight on Canada. What's that all about? I don't know. The resistivity. What is the resistivity? An electrical property of the material. And the CO2 measurements were taken along the core as shown. Resistivity is related to a sediment's particle size, compaction, and mineral composition. Table 1 shows the average percent sand, silt, and clay contents in the descriptions of various tills. So here's what basically they're saying. You got Canada. And so there's a maple tree over here. How do you do a maple tree? Something like that, a red leaf, right? And you got a moose, because it's Canada. And you got people saying A a lot. How's it going, A? And they took a core sampling, so they dug down. And they took out this core out of there. And what happens is there's these layers of stuff in there. And so they're just looking at all the different layers. So there's, if you go 100 meters down, or 10 meters down, you'll have brown till, and then you go 20 meters down, you'll get to your gray till, and you get to 30, and all the way down to 100, and past 100. So they went all the way down to like 110 meters underneath the ground. And they basically like put a drill bit that's really long and then just took that whole pipe out and are dissecting that. You know, they're looking at this. So here's the resistivity of the things. And notice how the resistivity changes, which kind of means you're at a different layer. And also the CO2 content changes. Got it? Alright, table 1 shows the different amount of stuff that they have. So in the brown layer, they got 54% sand, 31.7% silt, and 14.2% clay. Got it. Alright, on to the questions. A sample of gray till was recovered from another core taken in a nearby area. The table below shows the following analysis of the sample. Here's the sand, silt, clay, and resistivity and CO2. Based on the data provided in Figure 1 and Table 1, the gray sample till corresponds most closely to which till in Figure 1. So, which of these closest represents this? Look at the first number, 31.5. Which of these numbers is closest to 31.5? Do I even have any students in here? Did you guys all leave, or? Alright. The 31.7, the gray. And look, the gray matches up with, it matches pretty closely with our silt is 33, alright, and our clay is that. What about the resistivity? Resistivity of gray sea till is about what? It's about like 80 something, right about here. What was their resistivity? 80. I think that this stuff is gray till C. That makes sense. Alright. Okay, so part number 37. According to Figure 1, the oldest glacier advance in the area deposited of the following till layers is which? Okay, so the oldest one is what? Well, it's bedrock, but that's not an option. And then sand, and then gray till D, and then gray till C, because it gets younger as you get higher. So bedrock's not here. And sand. So gray till D is the next oldest. See? Gray till D. What do you mean, why is bedrock only 50? What it's talking about is resistance. It's talking about resistivity, which is a property of particle size, compaction, mineral composition. Maybe the properties of the bedrock happen to not give it very good resistivity. According to Figure 1, which of the following statements... see, that's the thing. With the ACT, you're not asked to analyze it. You're not asked to give your opinion. You're asked to say, well, based on the data, why do you think that? Like, it didn't ask us to say, well, why do you think hummingbirds actually went up in population? All it asked us was, what happened to the hummingbirds? And we said, oh, they increased in population. They didn't ask us to say why. Why did they think? I think it's an interesting thing, though. Like, I don't know. I don't know why bedrock has 50 ohm resistivity. It just does. And that's what the chart says. So I'm just going to go with it. Yes, the ACT test is not really a test to see how well you know science. It's a test to see how well you can read a chart. This is what I'm trying to say to you. Don't freak out when you get these kinds of tests, because it's not really testing you on... It's testing you on your logic, which is a good thing. It's a good test. I like it. But anyway, in Figure 1, which of the following statement best describes how the resistivity of sand and gravel layer compared to the resistivity of till layers? So, look at the resistivity. Compare sand to all the other tills. These are the tills. There's sand. What can you tell me about the resistivity? The resistivity of sand and gravel is up here. Compare the resistivity of the sand to the resistivity of all the other tills. What can you tell me about it? Can you guys not hear me? Is my audio bad? Let me try this. Can you hear me better? Okay. So what can you tell me about the resistivity of sand as compared to the resistivity of the other stuff? It's bigger. So the option is it's higher or bigger. That's it. Alright. The average resistivity of a bedrock in the core of most is more similar to the average resistivity for which of the following till layers? Alright, so bedrock is, the resistivity is similar to what? Now, Vernon already pointed it out. Bedrock only has a resistivity of 50. What else has a resistivity of 50? The olive green one. Exactly. See? Resistivity of 50. So that answer is the olive green and gray till. Okay, good. The sediments being deposited at the present time at a site of a core was taken have a much higher CO2 content than any of the tills. Given this information, in Figure 1, the CO2 content and sediment recently deposited at the site will most likely have the following ranges. Alright, so look at this, check this out. Here's my different sediments, and there's no data for the surface sediment. But I'm reading it, and I find that it has a much higher, CO2 content than any of the other tills before. So what can I definitely say about it? It's bigger than at least what? If it's higher than anything I've measured before, then it's bigger than gray till A, or at least bigger than what, 35. So the answer is, it's got to be greater than 35, and that's it. Does that make sense? And that's it. And that's the end of the test. The end of this thing. There is no cliffhanger. I am done with this, folks. You are done. I am done. We are done with this ACT test.